Hi guys, today I am going to explain about the blocking temperature. Before I am going to explain about the blocking temperature, I would like to explain about the Néel relaxation time. That Néel relaxation time is denoted by tau n. See this Néel relaxation time denoted by, it is not clearly seems, this is like tau, this is tau. Okay, so what happened if I am taking a nanoparticle in an external magnetic field, then I found that there is a no orientation. Suppose this is the magnetic particle or nanoparticle. I am taking this nanoparticle in a external magnetic field, then I found that there is a no any orientations of this magnetic nanoparticles under the appliance or influence of the magnetic field. So what actually happened there? Suppose this is the magnetic moment, and what is the magnetizations of this particle is nothing but a this magnetic moment. The magnitude of this magnetic moment is nothing but a magnetizations of the particle. Suppose this both the things are put in between the external applied magnetic field. So what happened, before applying magnetic field, this magnetic moment is in the directions, but after applying magnetic field, this magnetic moment changed its orientations or change its directions. For this changing from here to here, when it required some amount of time, the time period is called Néel relaxations time. So once again I clarify, in Néel relaxations time, particle is fixed, but there is a flipping or orientations of magnetic moments only, but not the entire particle. Now I am come to the original topic. The topic is blocking temperature. Suppose in a nanoparticle, I would like to measure the magnetizations of that nanoparticles. That means measurement of magnetizations nanoparticle. For this we required some time period. Magnetization of the nanoparticles means what? The magnitude of this of the magnetic moment. That means every nanoparticle consists of some amount of magnetic moment. So that much amount of magnetic moment, that means that much amount of magnetization present on the nanoparticle. So for this we need some time to measure the all magnetic moments as converted is as a magnetizations. So for this it is symbolically denoted as a tau m. I am writing here, that is tau m. See this one, this is tau n relaxation time, this is tau m, this is the magnetic measurement of magnetizations denoted by tau m. That means tau m is the amount of time for which we are going to measure the magnetizations of the particle. Suppose there is a case in which the measurement magnetization time is greater than Néel relaxation time. So what happened? Néel relaxation time is a very fractions time, and measurement of magnetization time is also very fractions, but measurement of magnetization time is greater than, in our case it is greater than Néel relaxation time. Then at that particular time, suppose I am starting to measure the magnetizations of this particle, but this magnetizations time is more as compared to whatever amount of time required to fluctuate or required to flipping this magnetic moment is less as compared to measurement time. So it is flipping during this measurement time so many times, so we are not able to catch the at particular point, what particular point this magnetic moment is fixed. It is not fixed, it is continuously flipping during this magnetic measurement time. So we are not able to catch on a particular particular directions. If we are not able to catch this magnetic moment at particular directions, then we are not able to measure the magnetization, since during the several period of magnetic measurement time, the average magnetizations we are finding that average magnetic measurement magnetizations we are finding that is 0. Okay, so this state of this nanoparticle is called superparamagnetic state of the nanoparticle. Now I am talking about the another case. In this case, the measurement of magnetization time tau m is very less than Neel relaxation time. See, at the previous time I am taking the measurement of magnetization, very important point, measurement of magnetization time is greater than Neel relaxation time. So on this case, magnetization is completely 0 because we are unable to catch the actual position of the magnetic moment. In this case, the measurement of magnetization time is less than Neel relaxation time. So what happened actually? Suppose I am start to measure the magnetizations, but it is less as compared to Neel relaxation time. So it is blocked here. Okay, at the beginning we can catch here because at that particular measurement time there is no sufficient time to flipping this magnetic moment. Sorry, flipping this magnetic moment. So at the beginning we are catch the magnetic moment at particular time. That means that time is less than Neel relaxation time. So here is a magnetizations is non-zero value, means we are getting some little amount, but it is not exactly 0 because we are blocked here. At that point it is called the blocked state of the magnetic nanoparticle. So there is a one more condition. If at the third conditions, if I am taking the Neel relaxation time, means this is the time period is equivalent to the magnetic measurement time, means at what amount of time this magnetic moment is oriented, I am exactly taking that amount of time to measure the total magnetizations. If Tm means tau m is equal to tau n, then there is a transitions occurs between the superparamagnetism and blocked state, superparamagnetism state and blocked state. But in the fourth condition, suppose I am taking the time factor is constant, and temperature varies. So what happened? At some we are increasing the temperature slowly. We get at particular temperature that transitions is occurred between superparamagnetic state and blocked state, and this temperature is called as blocking temperature. I repeat once again, the blocking temperature means what? The superparamagnetic state where the magnetization is totally 0, and the blocked state of the nanoparticle where the magnetization is not totally 0, it is somewhat greater than 0. Then there is a transitions occurs at some particular values. That value is called as tau m is equal to tau n. But in this case I am fixed the measurement time tau m, but I am varying the temperature slowly. Then I am finding at some particular temperature the transitions occur between superparamagnetic state to the blocked state, and that state and the temperature is called as blocking temperature. Thank you very much. Naresh Sarkar here.